I'm speaking to you from ANSTO, and I recognize the Darawala Nation and pay my respects to the elders past and present. I extend that respect to Aboriginal and Torres Strait Islander people here today on that call. And it's my pleasure on behalf of the National Committee of Applied Mechanics, NCAM, of Engineers Australia, and the Australian Net Zero and Circular Economy Conference at University Sydney, to welcome you to the Applied Mechanics for Green Manufacturing. NCAM goal is to promote and disseminate knowledge about the applied mechanics and engage in all activities between academia and industry. Applied mechanics is used across a wide range of fields, from fluid, solids to fractional mechanics. And today we have the unique opportunity to have on a call experts in additive manufacturing, and we will discuss additive manufacturing for green additive manufacturing for green manufacturing. So our first speakers is Professor Gwenaelle Proust, Academic Director of Sydney Manufacturing Hub at University Sydney, and she will be talking about additive manufacturing as a solution for material reuse. Our second speaker, Dr. James Hodges, is the Research Director at AMRC Northwest, and he will be talking about additive manufacturing for a sustainable future, perceptions versus reality. I'm going to introduce our first speaker, Gwenaelle. Gwenaelle will talk for 30 minutes, then James for 30 minutes, and we will then have a panel discussion afterwards, where you can ask the question in the chat and I will read them, and hopefully our panel will be able to address as many as possible. So please start typing the questions during the presentation. So Professor Gwenaelle Proust is in our school, in School of Civil Engineering. She's a professor in materials engineering. She got her first degree, engineering degree, in material science in France. She was awarded the Master of Philosophy in 2002 and a PhD in 2005 from the Department of Material Science and Engineering at Drexel University, Philadelphia in US. She then did 2 years postdoc in Los Alamos National Laboratory in New Mexico before arriving in University Sydney. Her research aims at understanding the relationship between materials properties and their microstructure, and to improve material performance, ultimately leading to the energy saving and to safer, more efficient devices. Her research projects encompass investigation and modeling manufacturing processes of materials and the effect of mechanical deformation on microstructure evolution of metals, understanding the effects of complex loading, mechanical response of material to developing better performed composites by taking the advantage of individual properties of each component. Okay, Gwenaelle, please start your presentation.
Thanks, Anna. So I'm going to share my screen, and I'm also going to have to say that my final exam is taking place from now till 6:30. So I'm basically on call. If my mobile ring, I'm going to have to take the call. That means there's a problem with my final. So please apologize if I have to leave. Hopefully enough people that review the exam that there should be no issue. You should see my presentation now. Do you see the normal mode or the presenter mode?
Yeah, it's okay, presenter mode.
Okay. Thank you, everybody. So I'm going to talk about additive manufacturing as a solution for material reuse. And before I go there, I'm going to talk about first, what is additive manufacturing? So I took the definition from ASTM, the American Standard Society, that define additive manufacturing as a process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to a subtractive manufacturing methodology. That is what has been done in the past. So this encompasses a lot of things in additive manufacturing. And I have also added here the additive manufacturing wheel that shows the different things that need to be considered when people want to do additive manufacturing. So there is a method or the technology that needs to be used, the material that you want to use, what is your final application, and what type of input you're going to need to provide. So it's not like additive manufacturing. There is one machine that's going to fit all purposes. There are different technology, as I'm going to explain, and there is a lot of consideration that needs to be taken into account while people are going to find what is a proper additive manufacturing technology for their applications. So what are the advantages of additive manufacturing? So you can truly customize product attribute. So you could do a one part component, a single component, and the investment will be the same that if you do 100 component. You don't need to make a mold. You can change the shape by changing your 3D model. So there is no limited number of components that you need to make to have a return on your investment, because changing the shape, you will not need to change anything on the machine. It's a fast way to do prototyping and product development and refinement, small batch production. As I said, you can customize a lot of things. During the process, you can change your mind. You can have the design engineer or coming with new requirement, and you can remake it. That does increase the flexibility and help you to tailor product improvement for the applications. It's also a process that reduces waste during the manufacturing, because you are not doing a subtractive technique, so you don't waste material by machining it and removing from a block. Here, you're technically using only the material you need to make a component. You reduce the energy input usage for the processing. Some of the equipment that we have in our lab at the University of Sydney could be actually used if you were putting a few panels, solar panel on the roof, and you will be able to use the equipment. It's also a way that you're going to be reduces transport and storage requirements. You can only produce what you need and produce as you need, so that you don't need to think about your inventory and have a large warehouse for spare parts. So if we talk about additive manufacturing, I already mentioned there are different technology that exist. So here is according to, once again, the American standards, they have categorized 7 different technology for additive manufacturing. So the one that people are most familiar with is material extrusion, which is usually one that everybody has seen. Some people even have that at home, where you have a polymer filament that you're going to melt, and then you're going to deposit the melted material layer by layer and create in 3-dimension new object. There is different technique that exists now in material extrusion. You can do even metal material using this technology. You can even do ceramic using paste printing. So that's a large category. It's one category of additive manufacturing, but behind that, you have different technology that exists to produce different type of material. Then you have binder jetting and material jetting that are similar, where you're going to have powder material that is going to be encapsulated in some binding material. So binder jetting, you built your part inside a resin, for example, while in the material jetting, you only deposit the material that you need. But the principle is the same. You're going to have to cure this material and form the part. Powder bed fusion is another technology that exists both for metals and polymers, where you're going to have on a powder bed a layer of powder that is going to be, in the case of metal, melted using either a laser or an electron beam, and you're going to produce your part once again layer by layer. Directed energy deposition, this is a wire technique or a powder technique. You can use old technologies such as welding, for example, to produce 3D object now. So using a one process, being able to do directed energy deposition. That polymerization is when you're going to have the material you want. So this is either a polymer or a ceramic into a polymer slurry, and you're going using light or heat, you're going to polymerize your material. And if you do a ceramic, you're then going to need to debind, remove this polymer and do some sintering, but you can produce the same way a 3D object. Sheet lamination is another process that's really specific, used a lot or used mostly in space industry, where you use thin layer of material, thin sheets of material that you just apply stress on them and create an object in 3 dimensions. Those 7 technology is what have been defined at the moment as the different type of AM, but there is an 8th one that is actually under review right now, which is a solid state technique. So more to come. So this is, for example, cold spray technique or stir friction processing, which are solid state technique to make also 3D objects. And this is in the review and will be added in the future to the different type of AM. So as you see, there is quite different technology that exists, and depending on what you want to do, what's your application, you might find that one is going to be meeting your requirement. Before I continue, I want to mention that additive manufacturing is not here to replace all the other manufacturing technology. I'm not going to say that in the future, we're not going to use any more casting, any more rolling or any other processing technology. This is a new technology that allows us to produce components that we will not be able to make in the future in a single component, or this is a way to produce near net shape component that require little post-processing or machining at the end. So that could save energy in the process by reducing the amount of machining. That can reduce the waste by only using the material that you need. So this, from a point of view of, and there are also, technique that require less energy. So that from a point of view of being economical energy-wise, this is a good way, but you cannot do everything with additive manufacturing. So you have to find the application that is going to be requiring such technologies. Now, if we look at the forecast market for additive manufacturing, so here are the number for the US. And you see on the left, the first graph show you the predicted use of additive manufacturing according to the different technology that exists. And you can see that the prediction in this, there's going to be a growth. So this encompasses all metal, ceramics, polymer, composite material. While if you look at the right, this graph is only limiting itself to the additive manufacturing for metals. But you see also that metal is going to grow, but that's why the number do not match the two graphs. One is metal, the other one is all the material combined. Now, if we look at Australia, what's happening? So additive manufacturing is a hot subject at the moment. And here it's just a map that shows you that different universities and labs around Australia have invested in capabilities to look at additive manufacturing. So there are different type of technology all around those places. There is a lot of powder bed technique, but there is some more exotic thing that exists at one university and other at another university. But that being said, and for people from other university, it might be the time to have a national talk to see how we can advance additive manufacturing in Australia by combining our efforts all together and try to not compete with the same technology, but see what we can do to help each other and to stay on top of what's happening, because the additive manufacturing technology is evolving really fast. So keeping track of what's happening is going to require a lot of investment in the future. And I think we need to talk about how to combine our money and our knowledge and expertise to keep on top of things. But that's a discussion for another time. Now we're talking about circular manufacturing economy. So if we look at the traditional way manufacturing was done, so we were talking about linear economy where there was raw material production use and then a lot of waste. So that's not that they were non-recyclable. For some of those, I think they were just not recycled. And I think there has been a reuse economy that has been put in place in the past already, where some recycling has been happening to add to the production. But this was still not a circular economy. If we look what some of the government, and I know in Europe, they've put this objective to have a real circular economy for manufacturing, where production, use, and recycling are all together and raw material are added as needed, but there is no more waste. So are we going to be able to reach that? And how can we do it? And how is additive manufacturing going to help us? I just want to show you some example of what is already done in additive manufacturing in circular economy concept. So these are some products. So the first one on the left, so if people look at the Olympics in 2021 in Tokyo, if you notice where on the podium on which people were standing, these were actually 3D printing podiums, made from upcycled pellets. So I think they produced like 21 of those podiums, and they were all made from recycled pellets. There are a lot of companies, so I just show one example here, but there's a lot of companies nowadays that make glasses frames using recycled plastic. And they are making those frames by using 3D printing technology. This is about polymer. Can we do something with other materials? There is research being done at the moment. So I'm not saying this is already on the market, but research is being done to see if we can produce powder for additive manufacturing by recycling chips from machining. So all the waste that is produced during machining, can we make something useful out of that? For the moment, it was all scrap material with nothing to be done with. And people are looking to make something useful out of it, such as powder. And there is different project going on in that area. And what I'm going to present now is research that my group is doing at the University of Sydney on some specific project. So the first one is a collaborative work with Sandra Loschka, who is an associate professor in the School of Architecture at the University of Sydney. We also work with some people from the School of Chemical and Biomolecular Engineering at Sydney, and John Mai, Jordan Gerdis, and Yirong Wang and Todd Zhu were some students, and they were some students who have worked on this project. There are a few more that have worked, and a few more have started to work on this project. And what we want to do is, can we upcycle forestry byproduct? So we want to see, can we do something useful with this product? So what is the motivation behind that project? There is a lot of waste in the wood industry that is coming from timber mills or landfill from some engineering products, solid waste, municipal solid waste, or even furniture waste. Is there something to be done with that? So can we reuse that material? There is also some agricultural waste. So for example, macadamia nuts are produced in Australia each year 40,000 tons, and 70% of the weight is considered as waste because this is the shell that nobody eats. So what can we do with this material, this waste material? So wood plastic composite is not necessarily a new concept. It's been around for some years now. And there is some technology that have been used, such as compression, extrusion, injection molding, to produce those materials. So we want to see if we want to make something more complex in shape, can we use additive manufacturing as a technique to produce those components. So for this project, we use one type of technology, which is a fused filament fabrication technology. And the two main objectives of this project were to develop first a wood plastic composite filament using material waste, and also to create an aesthetic of timber, because we want the thing to be aesthetically pleasing as well. So first we looked at developing the materials. So we look at different source of waste. So we look at some hardwoods from Australia. We look at red gum, gray box, and we also look at macadamia nutshell. Although in this presentation, I'm only presenting results on the red gum and the gray box. Our material of choice at this moment has been ABS, because this is the most common polymer used in FFF, and this material can be recycled. So that's the idea behind this choice. We have looked at other polymers as well, polycarbonate, PET, but I'm going to focus on ABS. And because wood and plastic actually don't like each other, we had to add some binding agent. And here we look at two different types of binding agents, maleic anhydride and lignin. Lignin is also a byproduct from pulp or paper industry, and can be extracted and coming from waste as well. Although in this presentation, I'm going to only show data from our maleic anhydride binding agent. So we started by producing our wood flour using wood chipped of red gum and gray box, low-cost lab where we had a coffee grinder to make our powder, but that works. Then we dry our flour, sieve our flour to look at the effect of the size of the particles. And then we added ABS and maleic anhydride. We put that on a filament extruder, and we produce some filament from the red gum and the gray box. And then using this filament, we use a 3D printer, and we produce some specimen for mechanical testing. So these are all the specimen that a specific group has produced, and we've tested that. And what we noticed, so we compare the data with Laywood, which is a commercially available filament. And what we saw is that in terms of strengths, we were matching what was available in the commerce. Advantage is that our material was stiffer than what is available in the commerce. Same thing when we're using the gray box, it's not as strong, but still stiffer than the Laywood. In terms of stress, we saw that there is an effect of the particle size, especially for the gray box. For the red gum, it was less obvious. And we see that we were matching or surpassing the property from the Laywood, especially for the red gum material. So that's why in the future, we are going to be concentric on the red gum. So now if I look at the aesthetic, when I print wood plastic composite, that's what it looks like on the right. What timber looks is what in the left. You would agree that what's on the left is more aesthetically pleasing. That's what on the right. So now we want to see, can we produce something that looks like that? So what we did is that while we were testing the effect of processing temperature on the mechanical property of wood, we noticed that there is also a change of color of what we printed. And this is what was used as a strategy to reproduce the grain structure of the wood by changing the temperature. So I will pass you the detail of the algorithm that the student John Mai has written to go that, but basically at the end, this is what we were able to produce. So some thin panels where we had more of a wood aesthetic than what we had previously. Then we went to create also bigger panels with 3D dimensions, like more like thicker than what the previous one, and also changing the surface and still have a wood idea, which I think was also a success. I'm running out of time, so I'm going to talk fast about this second study, which is another thing that we're looking here with my collaborator Simon Ringer and my PhD student James Warner, where we want to look at strategy to reuse the powder in selector laser melting. So what do we mean by that? Is that when you do powder bed additive manufacturing, this is the component that you're printing. All that is powder that is being used but not melted. But we don't want to put that in the trash. We need to reuse it. So what we want to do is that what are the best strategy where we can put a system in place to first save energy, because remaking powder costs a lot of energy, costs a lot of money as well. And you wanted to know Anna, the price of a kilo of titanium. Here it is. We want to see how can we create a good strategy for reuse. So in the literature, we see that different strategies have been explored, and I'm not going to go in detail into that. The problem is that there is no consistency between the studies. They have been done in a limited number of reuse, and usually the powder property are not investigated. So the application of those results is limited. So the study that we want to put in place is develop a powder reuse strategy that can be widely used and replicated in industry, and to observe the property changes in part manufacturers with reuse of powders. And these are the strategy we're going to do. We're going to compare different strategy. I'm going to pass that. We're going to look at the powder during the different processes, characterize mechanical property and microstructures, and expected outcomes, have a consistent comparison that we can really establish a technique to best reuse powder. So I'm going to conclude, and I'll be on time. So additive manufacturing, we see offers possibility for reduction of waste, reusing waste, and therefore we're going to be a step closer to reaching this circular economy framework for manufacturing. But can this be done while saving energy and be environmentally friendly? So what do I mean by that? Is that if we want to make powder for powder bed manufacturing, making powder takes a lot of energy, takes a lot of time, takes a lot of money. How is that a process to try to transform scrap into powder going to be economically advantageous? Also, if you look at the ship from machining, they're usually full of oil because that's what you do when you machine. So you need to clean them. What do you do with the cleaning process? How are you going to get rid of this water? So there is a bit of thing that I'm not saying it's not possible. I think there's a lot of things to be done still to make all this process energy economic and environmentally friendly. Before I stop, I would like to acknowledge the micro timber grant that we got with Sandra from Forest and Wood Product Australia, and also the Sydney Microscopy and Microanalysis and Sydney Manufacturing Hub for their help on these projects. Thank you.
Thank you very much, Gwenaelle, for this very interesting perspective on additive manufacturing, especially utilizing wood and printing and also metal 3D printing. I think that is a good introduction with metal to our next speaker. Please hold the question and put them into the chat so we can ask them in the end of the presentation. Can you stop sharing? James, can you start sharing and I will introduce you? So Dr. James Hodges will talk today about additive manufacturing for sustainable future, perceptions versus reality. James works at the University Sheffield's Advanced Manufacturing Research Center, AMRC Northwest, is a new expansion of internationally renowned AMRC group. With more than 20 years in advanced manufacturing research and development, James began working at the University of Sheffield's AMRC with Boeing at 2002, specializing in the analysis of surface integrity of machine aerospace alloys. Before his current role, James held a position of the director of the UK's National Metals Technology, a research and support center established to help metals and related engineering companies. James received his PhD from the University of Sheffield, is a fellow of Institute of Mechanical Engineers. Current research interests include powder metallurgy and additive manufacturing. Today, James' publications have won annual prizes from the Institute of Mechanical Engineers and investigators on life research projects over the £10 million. So we're very excited to learn more what AMRC and you, James, doing in UK. Thank you very much.
Thank you, Anna. Well, I'm delighted to be here. Thank you for inviting me. Hopefully the technology will work all the way across the world. So good afternoon, Sydney. Good morning from the UK. I'm just going to talk to you a little bit this morning about, check my slides are working.
Everything is working.
Yeah, okay. I'm just going to talk to you a little bit this morning about additive manufacturing and sustainability. What are the realities and what are the myths out there? There's a lot of hype around additive manufacturing still. If anyone's seen the Gartner hype curve, I think we're very much still in the peak of expectation at the moment. So just wanted to talk a little bit about what are some of the drawbacks and some of the myths out there. So this is mostly from a UK perspective, so please bear with me. Okay, so you might be wondering what the AMRC is. AMRC stands for the Advanced Manufacturing Research Centre. As Anna mentioned, we've been going for around 20 years now, helping industry with their research and development challenges. We're involved in anything advanced manufacturing, from machining technology through to composites, automation, Industry 4 digital technologies, and my own area, additive manufacturing. So we're very much about solving industry problems, not just academic research interests. So we're very focused on what are the current challenges out there. We're currently about 600 staff, and we cover all these different disciplines. Excuse me. We're also part of the UK's high volume manufacturing catapult network. So that's a large network of research centres spread across the UK that's similar in nature to the German Fraunhofer Institutes. So a bit of scene setting in terms of the background. The UK have set some fairly ambitious targets for net zero that they've actually written into law recently, dating back to I think it was 2008 originally when they started coming into law. But it's a commitment to reduce greenhouse gas emissions to 100% below the 1990 levels across the whole economy. And purely from a manufacturing industry viewpoint, that's quite a difficult target to hit, because UK manufacturing accounts for approximately 11% of greenhouse emissions. So apart from eliminating greenhouse gases, if that can't be achieved, then there must be a way of absorbing the equivalent amount. And this is the targets that are being set for industry to meet. And as you can see from the roadmap there, confusingly, they switch interchangeably from 2018 levels and 1990 levels. So as you can see here, 2030 is a 50% reduction from 2018 levels, which equates to, I think it's approximately 68% of 1990 levels. But relevant to industry, you can see in the bottom of the roadmap there is maximise energy, resource and material efficiency. So these are some of the things we can look at today in terms of advanced manufacturing R&D. We can look at, what are the processes out there that we can help reduce this number? What are the efficiencies we can make with industry to make sure that they can actually hit this target in the next 8 years as it is now? And as you can see, all the way down to 2050, 90% reduction, which equates to 100% in 1990. So some quite stiff targets to meet there. A lot of industry are looking for technological solutions to help them achieve this target, and that's where we come in with some of our research. And if you break that down, there's basically three scopes that are relevant to the manufacturing industry. You've got the scope 1 emissions. These are the ones companies can have direct control upon. This is directly generated emissions that the company can either reduce or eliminate entirely. The scope 2, harder, this comes from your energy mix, depending on your supplier. If there's a lot of renewables in your energy mix, then invariably your emissions are lower. If it's a lot of electricity generation via coal, burning of coal, then obviously they're going to be very high. So that's something that's harder to control, and it depends on your region in the world, to be honest. And then there's your scope 3 emissions, which is in your value chain, in your supply chain, harder to control, and even harder to quantify in some ways. However, these are the critical bits in terms of making sure that you can actually hit your target. And it's very, very difficult to make sure that you're not offshoring the problem to a different region of the world. So this is very much something to be aware of and comes into the conversation when we're talking about sustainability. Okay, so background to additive manufacturing. I'm not going to labour the point. I think you've already heard this, and it was very eloquently delivered. So again, it's adding material layer by layer to produce your component. 3D printing, additive manufacturing, interchangeable terms that are used regularly depending on your background and your want. And again, as mentioned before, 7 main areas currently. However, there are some new ones coming out there, and I'm going to touch a little bit on certainly the additive friction stir deposition towards the end. So again, you put your CAD model in, you put your material in, you introduce some energy, and out pops your part at the end. Very simple, very straightforward, very low waste, theoretically. And again, points are already being made very clearly. What are the advantages? You do have a lot of additional functionality you can put into your components, a lot of geometric complexity you can add. So a lot of lattice structures, lots of generative design to get these very organic shapes that spread load whilst allowing lightweight and weight reduction. You don't have to have large batch productions in terms of generation of tooling and then the creation of a minimum order quantity. You can go as low as you like. You've got a lot of flexibility, and this is where we see a lot of our industrial partners are particularly keen. You can really condense that development cycle down in terms of if you want to create a new component, you can go from CAD to build very quickly. And if you want to iterate that design, you can do so very quickly. So a lot of flexibility in there, and that's one of the real key advantages. You can also manufacture at the point of use. So your supply chain can be shrunk down. You're not having to transport parts from around the world. You do obviously have feedstock material you need to be aware of, but where you've got a method of production, that's where you can manufacture. As mentioned, not so much on the specialized tooling and fixturing. Obviously, there are some requirements, but compared to traditional manufacturing, very little indeed. So reduce cost in that respect. And waste reduction, particularly with expensive materials. Obviously, the figure of $400 per kilogram for titanium powder, that's very expensive material. You don't want to be wasting that or throwing it away if you have to. So a lot of potential there for recycling as well. In terms of the AM market, already been touched upon, predicted to grow from 15 billion overall this year up to I think it's 85 billion in the next 10 years. So massive expansion, lots of opportunities, but it's not all roses, unfortunately. Bit of a survey here from aerospace and defense industry, one of the big uptakers of additive manufacturing at the moment. As you can see, where it really works is being able to lightweight parts, and this is where companies are really interested in terms of where they see the benefits for this. Any weight that can be saved on an aircraft is therefore worth its weight in gold, so to speak. You can have better performance, you can have increased range. So looking to take advantage of the fundamental advantages of additive manufacturing in terms of lightweighting is a key driver there. But there are other ones as well in terms of, you know, sort of